welcome everybody to today's Monash Biomedical Imaging webinar with Professor Tsuchiya. And at the beginning of this webinar, I'd like to acknowledge the people of the Kulin Nations on whose land Monash University is positioned, and I pay my respects to the elders past, present and emerging. I would like to remind everybody to hold your questions, that you can ask questions throughout today's talk using the Q&A function in Zoom. The chat function has been disabled, so if you have any questions, just add them to the Q&A section and we'll come to them at the end of the webinar. So it gives me great pleasure to introduce Professor Tsuchiya from the Turner Institute for Brain and Mental Health Research. He's also head of the Monash Neuroscience of Consciousness group at the Turner Institute. And his research focuses on consciousness and the relationship between attention and consciousness. And today he'll be talking about integrating theory-guided and data-driven approaches for measuring consciousness. I'll give it to you now.
Thank you, Sharna, for introduction. And let's see. So, do you now see the slide?
Yes, we do.
Okay. All right. Thank you, Sharna, for introduction. And today I'm going to talk about this topic on integrating theory-guided and data-driven approach for measuring consciousness. And at the bottom left, I'm showing a short video clip of what this the talk is about mainly. And on the top right here, you have you see QR code. So for the paper that I'm showing on the bottom left, and also slide link, and also link to our YouTube website. So if you take a picture of or screen shot of this, then you'll get everything basically. All right. So outline of the talk is the following. First, I'm going to go quickly about the background on the recent consciousness research, and then especially paying attention to the studies of loss of consciousness. Then I'll introduce a data-driven approach via so-called HCTSA, highly comparative time series analysis. And then also introduce a top-down approach, this problem of loss of consciousness via integrated information theory. And then finally to discuss how to integrate the two to make progress. So brief tour of the background of the consciousness study. The most famous kind of starting point is René Descartes in the 17th century, who kind of recognized the problem of mind and matter. And then he argued that we should study scientifically on the matter side, but not the mind side. But the left out, side of this mind part is mainly my interest, and also many of the researchers in Turner Institute. And the core of this, I would argue, is the mystery of consciousness. How does the mind arise from the matter or brain? And this currently has a quite a broad and deep impacts from the basic science to the applied science. And the right side is this recent review paper, opinion paper by Dehaene, talking about a possibility of artificial consciousness in the coming years, or maybe 10 years. And then also empirically speaking, not only these kind of empirical scientific impacts, but some theories of consciousness are making precise predictions to make some empirical progress. And this is a sort of scheme of comparison of the prediction about particular type of conscious experience and its neural correlates produced by or predicted by two different theories of consciousness: global neural workspace theory and IIT. And in fact, not only these two theories that I highlighted right now, which is this global neural workspace theory here by Stanley Hain and also Jiro Tono's IIT. But there are a bunch of theories around right now, and there are at least 10, but many more than that is available as a theoretical option of consciousness. And leaving aside these theoretical issues, the current clinical issues are at least there are two important clinical issues with respect to loss of consciousness. This is a figure from famous 2006 paper published in Science by Adrian Owen and their colleagues, which was followed up by Monty and so on several years later. So the claim here is that maybe there are some proportion of the brain damaged patients who appear to be completely non-conscious from outside, and then clinicians and also nurses test various kind of behavior response to various stimuli and then determine whether they are in a coma state or vegetative states or unresponsive states or minimally conscious state right now. But potentially misdiagnosis can be up to 40%. And this particular person's case was initially diagnosed as a vegetative states, but when some of the patient's family and also doctors, nurses suspected that this person may be able to do something that no other vegetative patients can do. And in fact, this patient case, when he was asked to imagine playing tennis or navigating through the hospital environment, he was able to distinctively activate different patterns of the brain, which was very similar to normal, healthy controls brain pattern, despite the fact that his brain was quite damaged, like here, frontal area was quite damaged, and so on. And another issue is about the intraoperative awareness. If you have ever gone to general anesthetic surgery, you might feel it's kind of scary, but there is an estimate that maybe up to 30% of us who are supposed to be non-conscious during this surgery because of this general anesthesia may have something residual as a sort of a conscious awareness. And this has been demonstrated by the technique called isolated forearm testing. And here, if you cuff the arm at that location, this IFT cuff here, then it's for some reason which I don't fully understand. Well, you can possibly move your hand to report yes or no, and under this anesthetized state where the brain globally seems to be in the state of the anesthetized and unconscious state, if the doctor asks patient whether are you conscious or not, and then say yes or no, up to 35% of people can do this, yes or no, during this unconscious states. But the good thing about what we know about this is that nobody who was able to do this during the surgery remember that they were able to do this. So still, having said that, there is a possibility that you are experiencing something during the surgery, although you forget about it later on, is quite a concerning kind of thing, and it may be related to so post-traumatic disorders after the major surgery, or maybe to reduce even such a kind of possibility to have an overdose of anesthesia that itself can lead to the cognitive decline afterwards. So finding the appropriate dosage and also giving an appropriate diagnosis of general anesthesia and conscious state is a very important clinical issue. So for this reason, many people have started to work on this detection or discrimination of conscious versus unconscious states, or detection of consciousness using various kind of neuroimaging tools. This is one impressive study published by Engelman in 2018, Brain, where they compared the performance of the 28 potential markers of consciousness from EEG. And then they reported the best performance accuracy of the detection now is 0.77, with 0.5 as a chance, and the 1 is the maximum accuracy in discrimination. They looked at spectral feature, evoked feature, connectivity, information theory, and things like that, and then tested on this minimally conscious 177 minimally conscious people and the 66 controls and 148 uncontrolled, unresponsible patients. So this is a very large scale study, and then we have this as a sort of state of the art discrimination. And this kind of data-driven approach compared to other types of the approach that I'm going to talk about as a theory-driven has both pros and cons. Data-driven approach has an advantage in theory neutral, but if they test only few features, then it's very subjective in which features of the aspects of data to test as a discriminating conscious or not. And then, as you may know, because of the publication bias, people may report only the ones that worked, but didn't report the ones that didn't work. And we don't know whether there is this kind of baseline success rate or not from the features that has been reported. So that may lead to the difficulty in replication. And without any theory, it's also hard to understand why this particular feature, such as information theory or connectivity measure, may work. So that also leads to the difficulty in generalizing or predicting what will happen for let's say testing or obtaining some measure based on the sleep versus wakeful states to make a generalization between wakefulness to general anesthesia or brain damage, loss of consciousness. And then on the other hand, there is a different kind of approach, such as a theory-driven TMS-EEG paradigm. So this TMS-EEG paradigm was inspired by a theory of consciousness called IIT, Integrated Information Theory. And originally, they proposed that the level of consciousness should be supported by the differentiation and also integration at the same time. And so that means that the opposite, the loss of differentiation or the loss of integration should correlate with the loss of consciousness. And to measure that, what they did was that to stimulate the brain in particular area and then measure the response to the TMS pulse using EEG. So it's a simultaneous TMS-EEG experiment. And if they did it, then they can sort of operationalize what is the degree of the differentiation or degree of the integration by coming up with some kind of index. The problem of this approach is that it's a bit bulky and also expensive. TMS and EEG are not really, friendly for the our cheap device at the moment for any hospital. EEG is, so it's a bit difficult to implement across states, for example. And also, TMS EEG is inspired the kind of measure from the IIT, but it's not the direct test or direct measure of the integrated information, which was predicted by this theory per se. So there is some, approximation, proxy nature of this measure. So as a way to make a progress forward, our solution is to integrate these data and theory approaches. And this project has been promoted through mainly by Ben Fulcher, my colleague in the University of Sydney, and also Angus Leung, postdoc in my lab. So the first component is a data-driven approach to make it really extensive. Ben has been developing this toolbox called highly comparative time series analysis, or HCTSA. And then also we recently developed this another toolbox called Python for statistics for pairwise interaction, PySpy, developed by Oliver and Ben and Joseph. And then on the other hand, we also promote this theory-driven approach But rather than doing this approximation methods, we directly try to compute the integrated information and its structure. That is also important kind of concept in the IIT based on this computational methods. So the goal of this project overall is to compare them in a way that is in terms of the accuracy of out of sample performance. And also try to kind of generalize it across etiologies of the detection of loss of consciousness. So that leads to this initial our kind of try of this HTSA approach on sleep EEG data. So here what you are seeing is this explanation of traditional sleep classification. So previously, sleep researcher was looking at this EEG pattern over 30 seconds and then look for the feature that characterize this non-conscious state, probably 50% of the time in non-REM sleep stage 2. And its occurrence of spindles or K complex was one of the features. And then it's based on basically visual features. And it's unclear whether there is a biological basis for that. And then novel framework using HETSA is to subject this 30 seconds data into this toolbox of HTSA, which has 7,000 different kind of methods, and that gives us 7,000 vectors of the outputs from this 30 seconds data. And that comes from data distribution, spectral power, model fitting, and the auto-mutual information, predictability, graph analysis, complexity, and so on. And then out of that, data set, you get this 7,000 vector. And then based on this, we can use various kind of, unsupervised technique, but in this particular paper, we use a K-means clustering technique. And then identify whether we can actually see sleep pattern emerging. And in fact, we were able to do so. That's sort of the paper story. And this is a collaboration with Nicholas, Cao, and Jasmine, who are sort of student, and then Ben and Thomas, Jenny. Thomas and Jenny are the sleep researcher at Monash. Thomas now left for Paris to get his tenure job. So just to summarize, traditional visual scoring method of the sleep staging, which is still currently dominant, is to visually identify what is a characteristic of the wake state or N1 state, N2 state, N3 REM sleep over 30 seconds of the period. The reason why it's 13 seconds is weird, and it's quite outdated, I have to say, because when sleep classification was invented, then at that time, this polysomnography paper system produced this output over the 30 seconds, and then that's roughly the same size as the A4 paper. And then it goes to the next page, and that's sort of another 30 seconds. And because of that, the sleep scoring was based on 30 seconds. But it's also understandable why they didn't want to make it even longer or shorter, because of the fatigue and also practicality of the sleep researcher who scores it. But anyway, and then classification method can use some kind of magnitude or a proportion kind of information as well, and then sleep stage is eventually kind of defined by subjective way. And then on the other hand, our sort of the scheme can take many different kind of features that may not be visible to human eyes quickly. And also the classification or clustering is potentially driven by the data itself. Data can speak for itself. And we don't need to restrict ourselves to 30 seconds, and as the computational power are available, much shorter ones are totally fine. And then epoch by epoch classification allows us not to can discriminate, discard the contextual information, but also allows us to discover a sub-stage of the sleep as well, which is also going to be important in the future. So this is one particular example of a subject's data for one subject. So this is roughly like 8 hours of sleep data from one particular subject on open data set. And then he goes from wake state to N1 to N3 to N3, like initial 30 minutes, and then come back to wake state, and then goes to REM sleep roughly like 4 hours after that. And then what you see at the top is the output from the HCTSA features. Some of them produces invalid values, so we filtered it out already. And this is, by the way, only one channel in the EEG parietal areas. And then what you notice is that without really doing any kind of fancy analysis, it's quite easy to see that this correspondence, there's some kind of global correspondence between what humans agree to label as, let's say, N2, and also what the pattern of the feature looks like. And the red is like positive value, and the blue is negative value, normalized across all the features. So, for example, when the people agreed to be in the N3 here, then the pattern of the features look like this, and also in a separate time point, they also look like quite a similar kind of feature pattern. On the other hand, when there is a REM sleep stage here, then there is a sort of distinct pattern here. But there is also more than that. As you can already see, there's a stripe pattern within REM. That means that there is potentially some kind of sub-stage of the REM, but it's lumped together into one REM according to this current classification. And similarly, also during the N2 stage, in here, experts agree that this is mostly N2, but subject just occasionally produce some kind of signs of wakefulness. Maybe like just waking up, opening eyes, and then momentarily awake, but we forget about it or something like that. And then that's captured by this HCTSA's feature vector. There's some kind of notable stripe here. Also, here as well, and also here. But it also detects something very similar here, which is missed by experts. So there's something that maybe this kind of machine-based analysis can help or complement the analysis by the humans. Okay, there was a question. Just be curious, using deep learning method for embedding time series to latent space and performing clustering could have been good. Yeah, so we can do deep learning analysis or any different kind of sleep based analysis, but we can talk about it later. Our initial goal of this project is not to replicate human-based classification, which has been done a lot. And also there are many different kind of algorithms that can do that. But what we wanted to do with this study is to discover the way to go beyond human classification. So discovery like this sub-staging like structure within REM or missed wake state during the N2 is actually very important. And if you start to do that with a deep learning supervised analysis, we cannot do that. So we want to avoid that. But anytime any people can try that as well. All right, we can come back that later at the end of the presentation. And if you have any question like that, I can take it as well. All right. So not only this kind of over time kind of analysis, we can also look at just by collecting one subject's N2 stage across all the time, and then try to see what kind of shape in terms of the distribution we see. So here over the roughly like 1 hour or something like that, we can collect N2 from one particular subject, and then if you align the time course with respect to similarity of the HETSA features, then you see immediately like 1, 2, 3, 4, 5 kind of clusters just based on the EEG. And we one channel of EEG, so we can do much better in the future. But anyway, so as you can see that this particular episode of N2 is very unlikely to be the same as this other types of N2, and also this one as well. But it's currently lumped into together. And if you do some kind of dimensional, lower dimensional representation of this, among the 12 subjects we looked at very carefully, pretty much everybody showed this kind of distinct cluster within N2. So something like here for subject 439 and subject 001 has this cluster. And N2 state has been proposed to have different sub-stages in the previous researchers, sleep researchers, but it's not been uptaken by the general sleep researchers, or rule hasn't been changed, partly because it may be difficult to gain some kind of physiological insight from that. But automated analysis and also big data analysis like this will open the new future for this type of study. Also, one important aspect to point out with N2 with respect to consciousness research, which is my interest, is that N2 is if you are woken up during the N2 state, then 50% of the time, pretty much everybody can report what you are dreaming of. But it's a type of the dreaming that is very different from what you remember in the morning. It's not like a narrative. It's a very short usually, and also very simple. Like I was in the savannah, or I was in mountain, or I saw a cow, or something like that. And but this 50% of the presence of the dream may be correlated with this pattern of this substaging, which is something that we are interested in testing in the future. Okay. And then another thing is a data-driven loss of consciousness due to sleep, is that the traditional sleep stage classification method is outdated. And so, we are proposing to further optimization in terms of substages, and so individual tailoring, and also data lengths and so on. And I mentioned about the dreaming stuff, and also sleep misperception and hypnagogic states is also another different kind of the directions. And then there is a theory-driven component I can talk about, and this. Sharna, can I talk a bit more, or should I stop here? Or
I think you're fine.
Fine. Okay. So then, just briefly, integrated information theory predicts that loss of consciousness is probably mirrored in terms of the loss of the structure of the consciousness, and especially integration will be lost. And the key idea here is to compare the intact sort of system with a virtually disconnected version of the system. And skipping all these kind of small details of the how to compute this, Angus was able to compute this integrated information structure, at least from the fly local field potential recording, and then show that the wake compared to anesthesia has a much richer and also bigger volume kind of integrated information structure. And this is a decoding accuracy and so on. And then I'll just skip this. But how can we compare IIT with other types of the analysis? Data-driven analysis has been unclear, and we need to use same data and so pre-processing to address these things. But also there's a difference in terms of the nature of the analysis. HETSA is always univariate, and integrated information is always multivariate. So one possible thing we can do is to try to register the prediction from the univariate or bivariate IIT in a way that is based on the preliminary data, and they make a prediction into the unseen future data. And that's something that Ben and Angus, in collaboration with Bruno van Swinderen and their student, to do this in a pre-registered manner. And I'll just skip here. But then the sort of the remaining component of the comparison is that the IIT is multivariate and also has lots of approximation. But this, data-driven method so far has been limited in a univariate analysis. So to make an HETSA-like toolbox, but for the bivariate analysis, Oliver and in collaboration with Joseph and also Ben, we started to construct this bivariate version of the HETSA. So here we collected lots of bivariate analysis available on the web and also in literature, and then constructed this 250 different kind of bivariate analysis, which takes actually quite a bit of time even to apply for like 30 seconds of the data if you try to compute for all possible pairs of the neural recording. But applying this to 7,000 or 1,000 multivariate data set, we were able to find some kind of clustering of the bivariate analysis. And then we see some kind of similar behavior across some of them time consuming, some of not time consuming kind of measure of the complexity or bivariate interaction. Of interest to us is this measure of the integration, integrated information called phi. There are two kinds of phi that can be computed on just a bivariate data, phi star and also phi g. They turned out to be similarly behaving compared to Granger causality or spectral version of a Granger causality compared to all the other bivariate analysis. And this is exactly theoretically predicted, but it's also interesting to see that their similarity is relatively limited. That each of the line is not showing that it's not super correlated, but a different version of the phi g or different version of the phi star is highly correlated, as also expected from the theory. So using this and applying this to the loss of consciousness data, then we can start to compare theory-driven versus data-driven type of that approach for the detection of consciousness. All right. So to do that fairly, we think that it's very important to do the blind detection and the blind kind of classification for the consciousness experience classification. And fixing the pre-processing parameters is very important. And then report the results regardless of the results. So we need to do that in a registered report in by blind manner. And then finally, we want to do that also across etiologies. It's not enough to find sort of the index that measures or discriminates between the general anesthesia versus wakefulness. If you want to understand the sort of the core feature of loss of consciousness, we need to compare that with the brain damage data or sleep related loss of consciousness. And if we find some common component that is common to many etiologies of loss of consciousness, that would be a great finding. So in summary, I showed in the first part that data-driven approach can characterize neural activity from different angles, either 7,000 univariate analysis by HETSA or 250 bivariate analysis in PySpy. And also theory-driven approach requires still some kind of development, but we can already start to compute the predictability of the loss of consciousness by following some algorithm. So to understand this complex experience of the consciousness itself, it's not that never like single scalar, but it's more like structural kind of characterization is necessary to characterize consciousness at any given moment. We need to utilize this type of the rich computational tools. And with that, I want to thank for the NBI for invitation for this talk. And here's my current lab members and also collaborators. Thank you very much.
Okay, thank you now for that fascinating presentation. So for the audience, I encourage you to add your questions and comments to the Q&A feature of Zoom. So Shenzhen just has a follow-up question after his deep learning question. So in this case, mainly the self-supervised methods could be used for finding a latent space that might better capture the multivariate time series information as a deep learning based data-driven method. So he's not talking about a fully supervised learning framework that needs human labeled annotations.
Yeah. So I totally agree. And in a sense, this, TSNE is one way to visualize sort of this kind of unsupervised clustering, but also, we haven't tried other, unsupervised or self-supervised type of the technique. So it would be interesting to apply something like that. Yeah, I agree.
Cool. Now, I had a question. It was actually, I was looking at your earlier slide where you had this carpet, similar carpet plot, but yeah, this one here. So I was just wondering, is this for a single subject, right?
Yeah, this is the subject.
So I'm just wondering how reproducible this analysis is across subjects. So is it the case that sometimes this just doesn't work for some subjects, or is it like highly robust to individual variability?
So in terms of the correspondence between ASM labels and feature-based clustering, it's quite actually robust. But also, it's not robust in the sense that there is this kind of kind of mismatch within N2, for example. So here, if we impose the cluster decision of these 5 different ways, so in fact, this is actually one preliminary way to do it. But within N2, if we ask the classifier to make 5 clusters, and then this part is actually close to REM sleep, and this one is close to wakefulness, and so on. So depending on how you define or what's the purpose, it's not super clean in a sense that it is corresponding with human levels. But so that's one answer. And then in terms of the reproducibility, it's very interesting, and I'm very interested in doing that, to apply this technique for the same subject, but across multiple nights. Because it's likely that this kind of transition from one state to the another repeats within the subject, but may have a different kind of characteristic across subjects. And if we can reproduce that kind of dynamics across nights, that would be quite reliable.
Yeah, that'd be really cool. So audience members, please ask your questions. I just had one. It's actually not related to what you presented today now, but sometimes with some consciousness research, I sometimes wonder if what people are actually looking at is attention. And I guess my understanding of how attention and consciousness differ as theoretical constructs is not particularly clear. So would you mind setting me straight on that?
That's actually one part of my one of my big pillars of my research, the difference or similarity between the attention and the consciousness. And yeah, so it's difficult to say, summarize in a few words, but for example, in the case of the level of consciousness, like this, many people confuse or confound, sometimes intentionally, between the arousal consciousness and the alertness. But from the presence or absence of the experience itself, that is a definition of the consciousness, I would say. So as long as you are awake and have some kind of experience, then you have consciousness. But when you are not alert, lower attention, then you may not be able to react to the stimulus outside. But that could be completely fully conscious, but just thinking about something on your mind, and then reduces sort of the responsibility to the other things outside, right?
Yeah.
And in fact, that's the sort of the phenomena that we studied and published last year with Thomas Andrion on the mind wandering and also mind blanking.
Mm.
And that's one way to, in a sense, dissociate consciousness. You are fully conscious, but attention itself fluctuates.
Yeah.
Right.
Yeah.
So that's one thing. Yeah.
Okay. Cool.
Yeah.
And Shenzhen just has one last question. Is it valuable to include other types of information, such as structural information, and combine it with the time series data as a multimodal data analysis?
Yeah, that's an excellent suggestion and question. I'm actually interested in doing something like that, but I don't know how to do it. So if you have an idea, that maybe we can chat about it later. But one thing we haven't done is that to think about this HETSA-like algorithm on the space, right? So many people, including myself, do not have a good idea on how to extend this type of, different kind of analysis over the, methods of the space.
Mm.
Most people use like PCA or ICA or like, I don't know, what else do we have? Like but each of them has a cons and the pros, and then there is some kind of correlation between these methods, but also there is an advantage into another method, right? So I think it's very important to work on something like that, but yeah, I don't know. So and integrating this with structure information without talking about structure version, a special version of the HETSA may be easier to do, but I haven't done anything like that.
Okay. We've got a question from Will. Is there anything separating consciousness and being awake?
Yes, so that's a good question. And here I want to first distinguish two types of the usage of the term consciousness, right? So if you're talking about consciousness as a level of consciousness, like from awake to anesthesia or coma or vegetative states, it's a kind of fluctuating levels of consciousness. That's what I was talking today. And then being awake as that kind of state is basically the same thing. But some people consider the state of the being awakefulness or being alert as has to come together with the capability to respond to the outside world or to report what they were experiencing. And if you start to include this kind of requirement, which is, I would say, not really essential for consciousness per se. As long as you're experiencing something, it is conscious. But if you require some kind of report or alertness type, response, then it might start to differ.
Okay. William has a follow-up question, which is quite related to what you were just talking about then now. So regarding the difference between consciousness and attention, wouldn't it apply that all animals that are awake are also conscious?
Yeah, so I would say that's if you define that way, I would say that's the case. And in fact, I skipped this part of the talk, but the data that we have been analyzing quite extensively is coming from flies. And you might say that insects cannot be conscious, but if you sort of relax the term conscious as the sort of the presence or absence of being in some states or not, then we don't think that flies are same kind of have conscious experience, like thinking about future or worry about the death or whatever. They don't do that, and they have a different kind of sense in each modality. But just being in a state of anesthesia or wakefulness or sleep or wakefulness, this kind of thing is likely to be similar to us. As you learn more about physiology and also more about the behavior of the flies, you'll be surprised, because even though they have like only 10 to the 5 neurons, which is much less than 10 to the 11 neurons in our brain, they receive this, if they receive the same anesthesia as humans, they lose the consciousnness in a similar way. And also their impairment in learning or social behavior is also impaired by sleep restriction in very similar way as humans and other animals. So we need more study to see how much of this analogy and also homology extends or breaks. But starting from your intuition that insects cannot be conscious is not I think good idea. That's my approach.
Okay, well, on that really fascinating point, oh no, someone might have just, William just said thank you. So thank you very much now. It was a fantastic presentation, and thanks to all of our attendees. I'll just encourage you to join us on the 28th of September to hear from Claire O'Sullivan from Alfred Health, Monash University and Newcastle UK University. They'll be speaking about peripheral airways and asthma, significance, assessment and targeted treatment. So I'll close off the webinar. Thanks very much now.
Thank you very much, Erna. Bye.